This is 2859. In this one, it's a circuit with two capacitors in parallel. And then they go down through a switch to a resistor. The resistor is 500 ohms, and the capacitors are 3 microfarads and 2 microfarads. And let's see, before the circuit is closed, both capacitors are charged up by a battery. So they don't show the battery, they don't really explain what the circuit was, but they're both charged by a 12-volt battery. So what that means, basically, is that this side of both capacitors is at 12 volts. This is at 12 volts, this is at 12 volts, this whole wire is at 12 volts, and this side is at 0. So it goes 12 all the way to here where the switch is closed, opened, 12 volts. With the switch open, they charge them up. When they take the batteries away, but the capacitors will hold their charge, and with the battery gone, they close the circuit. So the question is, after they close the circuit, they're going to discharge, and the question is, after 1 millisecond, what's the charge on this one, what's the charge on this one, and what's the current through that one, after 1 millisecond. So, the first thing to realize is that we can get started by recognizing this as two capacitors in parallel. So it has an equivalent capacitance. So the equivalent circuit is simpler. It's 500 ohms and a capacitor here. So 500 there. And this capacitance, when you have capacitors in parallel like this, they just add. So the equivalent capacitance is 5 microfarads. So we want to start thinking about what happens then to all the charge that was built up and how does it come off. And we want to know after 1 millisecond how much charge is left. So we know that when a capacitor discharges, Q goes as the original Q naught e to the minus t over RC. So Q naught, we know we had 12 volts across 5 microfarads, across a 3 and across a 2. So let's see what that is. That's a capacitance of 5 microfarads times 12 volts. So there's your Q naught, E to minus T over RC, where it's the equivalent capacitance. So R is 500 times 5 is 2500, but it's times 10 to the minus 6. So that's 2.5 milliseconds. There we go. So we can work on that a little bit more. Let's see, that's 60 micro there. That's 60 microcoulombs e to the minus t over 2.5 milliseconds. And we wanted to know what the charge is on each capacitor at a time of 1 millisecond. So we can actually go ahead and write in here the total charge as a function of time. We can go ahead and put 1 millisecond there. Right, so the Q at 1 millisecond. The charge at 1 millisecond is 60 microcoulombs e to the minus 1 over 2.5. And see what we get. Now let's see, so if you, with your calculator, put e to the minus, that's 0.4, e to the minus 0.4, and then multiply it by 60 microcoulombs, I promise you will get what? You will get 40 microcoulombs. Okay. So it started at 60 microcoulombs and with a time constant of 2.5 milliseconds, so by the time you go 1 millisecond, it's going to come down, roughly halfway. So there it is, 40 microcoulombs. But the question for part A was the charge on each of these individually. So the question is, how is this 40 microcoulombs divided between the 3 and between the 2? Well, in this case, we know that they have the exact same potential on their plates, right? They're always going to have the same potential difference because one side is connected by a wire, the other side is connected by a wire, and there's no resistors in between that could cause a potential drop. So as long as they have the exact same potential, then the charge will be divided by their capacitances. The one with the bigger capacitance will get more charge, the one with the less capacitance will get less charge, and it'll just be proportional. So we can basically say that if the total is 5 microfarads and this one is 3, then the charge on the 3 microfarad will be 3/5, will be 60% of that 40 microcoulombs, so it will be 24 microcoulombs. And the charge on the 2 will be, well, it's left 16 microcoulombs. It'll be 40%. So that's how we know the charge on each one. And the last question was the current in the 500 ohm resistor. So for that, we just take the derivative dq dt to get current, and what would it be? Let's see, so it would be I as a function of time is, well, that was 60 microcoulombs times 1 over, this is the t, times 1 over 2.5, so it'd be 60 microcoulombs over 2.5 milliseconds is how it's going to decay, e to the minus t over 2.5 milliseconds. And that's your di dt. Of course, this should come out to just be the initial current. That should also come out to be just 12 volts divided by 500 ohms. Should give the same thing. So if you do that, then you get 24 milliamps. 24 milliamps e to the minus t over 2.5 milliseconds is I of t. So I at 1 millisecond comes out to be 16 milliamps. Just by plugging in 1 right here, you get 16 milliamps. And that's all three, the charge, and the current at 1 millisecond.